marginal treatment effect. Today, I'm going to present marginal treatment effect with misclassified treatment. It's a joint work with two of our students here, Santiago and Kyung-hoon. So, measurement errors in treatment variables make identification usually difficult. So my colleague Brent Kreider in his restart paper wrote this. Even in the homogeneous treatment effect framework, measurement errors in a binary regressor can result in severe identification deterioration of regression coefficients. And a lot of papers have extensively studied the issue. But Takuya Urad, in his 2018 job market paper, appears to be the first to investigate the identifying power of an instrumental variable in the unobserved heterogeneous treatment effect case, when the treatment is endogenous and mismeasured. Mahajan and Lubel, they have allowed for observed heterogeneity through covariates, but not unobserved heterogeneity. So Takuya derived bounds, Ura derived bounds on the first bounds on the local average treatment effect when the treatment is misclassified. Okay. And since then, Calvi and co-authors, they propose a new estimator. So basically what they have in the framework, they have two surrogates for the same treatment that is mismeasured, that is unobserved. And they showed that they define a new estimate that they call Mr. Late, measurement robust late, and they point to identify the effect. The question is, what does Mr. Late measure? Usually it doesn't measure the true late, but they show that under some sufficient conditions, Mr. Late is going to identify the true late. So Yanagi showed that with some spatial regressors, it's possible to achieve point identification for the late when the treatment is mismeasured. And Tomasi and Zhang, they extend the result in Ura's paper and Calvi's to multi-value discrete treatment. So a closely related paper to us is the paper by my co-author Victor Possible, who derived complementary results in the same framework, similar framework to us, but he mainly allows for dependence between the instrument and the misclassification variable. We assume in our framework that there is the independence between the instrument and all the unobserved variables in the model, but we show how we can extend that to the case independence, but that's not the focus of our paper. So what we do in this paper, we show that in general, the MT will be partially identified, and we provide some tractable characterization of the identified sets. We show that under some mild regularity conditions, the sign of the MT is locally identified. Okay, and I will discuss this condition. They are usual, the same condition that you have when there is no misclassification. And more than that, we derive tighter bounds for the lates when the instrument is discrete. Okay, then I'm going to show you some illustrations. So since I have 15 minutes and maybe 12 left now of 10, I will show you the model and then present the results. Okay, so here's the model. We have an outcome variable y, okay, which is observed, and y1, y0, they are the potential outcome when someone is treated or not treated. D star is the true treatment variable that is unobserved to us. Okay, Z is an instrument that shifts the true treatment decision. Okay, the selection into treatment. Okay, so everything that is in red here is observed data. We have data on that, and everything else that is in black is unobserved to us. So we assume that the treatment decision is such that the cost is less than the benefit. The cost is the variable V. So it's a cost benefits analysis decision. So the individual will decide to take the treatment when the cost V, which is unobserved, is less than a function of the instrument Z. It's the benefit function PZ. We don't know the function PZ, but we observe the instrument. Okay. And now D is the observed mismeasured treatment. So epsilon is the variable that captures the misclassification. If epsilon is equal to 1, it means that there is misclassification. Then D is equal to 1 minus D star. Okay. And if epsilon is equal to 0, there is no misclassification. Okay. Then D is equal to D star. So usually when people look at this, they say, yeah, you are making an assumption. But what we showed in the paper is that when we take any two binary variables, it's always possible to have this representation. So this is not really an assumption. Okay. So it's known in the literature that when you have binary treatment or binary regressor, the measurement error is non-classical. Yes, actually it's non-classical. The measurement error here is the 1 minus 2 times D star times epsilon. And as you can see, there is a negative correlation between the true treatment and the measurement error. That is well understood. So what we're going to look at here, we're going to look at the MT, which is the expected value for Y1 minus Y0 given the cost, V. So it's the average treatment effect for people at the cost margin, okay? So we will try to identify this parameter here. So examples is the return to schooling example. Usually people under-report or over-report their education level, okay? They try to overstate that. And Black and Quarter, they document that more than a third of the US population, they claim to have a professional degree while they don't have such degree. But someone documented later that the definition of professional degree may be the reason why they misreport. Another example that we use is this COVID example, where you want to look at the effectiveness of masks, for example. Okay, young people, they think that okay, they have immunity, so if they get the disease, they will recover, right? So for them, the discomfort of wearing masks, the cost of wearing masks may be higher. So if you want to look at the effect of mask wearing on the effectiveness of in the fight against the COVID-19 pandemic, then the V here would be the cost of wearing masks, the discomfort that comes from wearing masks. Okay, but usually people may report wearing masks while they don't, and also people may wear masks and they will report not wearing because of some political reasons, right? But they know that they are sick, and the health condition does not allow them to afford getting the disease because they may be seriously sick. But then because of political affiliation, they may say, yeah, I don't care about wearing masks. So then wearing masks may be mismeasured. So what are the identifying assumptions? We have mainly 4 assumptions. Okay, the first one is that we have a good instrument, so that what I was saying in the beginning, the instrument is independent of all unobserved variables in the model. The second assumption is that the V variable, okay, is absolutely continuous, so that we can normalize the distribution to be uniform 0, 1. Okay. And the second assumption, which is also crucial, is that we have a continuous instrument. That the difference with the other papers that have looked at the local average treatment effect. Okay. So these assumptions are standard in the literature. If the epsilon is equal to 0, then we get the same, basically same assumption as in Hetman and literature. Okay. So this next assumption that we have is that we know some upper bound on the extent of the misclassification. Okay. So if we think about the schooling decision, you can get information from universities. They can tell how many people or what the percentage of people in the population that have actually a college degree. And then you can compare to what is in the survey and then get some bounds on the misclassification rate. So that information, we take it as exogenous. So you know that some upper bound in the misclassification rate. Okay. So the first result is that misclassification does not actually affect the local instrumental variable interpretation of the IV. So basically, the MT is still the derivative of the expected value of the Y, which is observed, given the PZ function, which is the propensity score that someone gets treated, the true propensity score. But the problem here is that the PZ function is not identified. If you don't have misclassification, the PZ function is the identified propensity score in the data, which is the probability that someone reports getting treated given the covariate, the instrument C. But here we lose identification because it's misreported. Okay. So what we do first, we're going to partially identify this, and we just try to use the condition to back out the distribution, the conditional distribution of V, the cost variable, given that there is misclassification and given that there is no misclassification. And this has to be CDFs, which means that it has to be non-decreasing, limit at plus infinity should be 1, minus infinity should be 0, and right continuity. If we use those conditions, we get these bounds on the PZ function, but they are pointwise sharp, but not necessarily functionally sharp, in the sense that if we take the difference of 2 PZ prime, the bound that you will get will not be sharp. Okay, so to get functionally sharp bounds, what we do is we consider to derive these bounds here, we only use the information from the first stage. Okay, so this is like a PZ is the first stage estimation, right? So usually you estimate the first stage and then you go to the second stage if you are estimating standard IV model. But what we're going to do here is like we get the first stage to get the pointwise bound, when we're going to use second stage to improve on the bounds in the first stage, which is a bit unusual. So the second stage is actually helping the first stage here. And why? I don't have time to show all the details, but here is what we get. The bound that we get on the PZ minus PZ prime. So this information here is like the total variations that you're getting from the data, combining the joint distribution of the Y, the outcome, and the treatment, okay? And that's the information you combine both the first stage and the second stage. And that helps tighten the bounds on the difference between PZ and PZ prime, okay? So I have, how much time do I have now?
It has been like 12 minutes and 30 seconds. So
okay,
we still have.
Let me show you the result, the main result here. So what we showed is like, if this ratio here, it's in the standard framework, when there is no misclassification, it's actually the ratio late, the generalized late, which is here. Okay, so if we assume that the limit exists, okay, that's the regularity conditions that I was saying in the beginning. And if there is no misclassification in the sense that the alpha bar, the upper bound is equal to 0, then we get the standard limit version of the MT as the limit of the late, okay? But if alpha bar is strictly positive, which means that you allow for misclassification in the data, then what we showed is like the sign of the MT is locally identified, okay? So we have this minimum between 0 and this quantity, and the max between 0 and the quantity here. So you can always sign the MT if there is misclassification under our assumptions, okay? So some illustration here. So the bounds we try to, so because of that, in this case, in the DGP, we always have positive MT. So that's why you see that this lower bound is always 0. So we get the sign, but it might not be sharp. And as you can see, whether it's the bounds are tight or not depends on the DGP and the specification, okay? So now comparing this to what exists in the literature about the late. So people usually say, is this like a limiting version of what exists for the late, the bounds for late? No. So if you look at bound for late in the literature, okay, Takuya's bound, they are like half of the summation of these two quantities. But our new bound that we get is the maximum between the two quantities, which means that we always have higher, okay, lower bound than his bounds. So we improve on his bound. And the framework is not different, okay? So that's the main thing that I want to talk about. Now, when we try to add more structure to the data in order to try to tighten the bounds, what we had when we don't add those structures, like we assume that the misclassification is exogenous, or we assume some parameterization, then we tighten the bounds. These are actually the bounds, and this was what we had before when we don't add these restrictions. Okay, so let me quickly say this about we ask a question: is there any situation where the standard MT that people have will be robust to any misclassification? So is there any situation where we should not worry about misclassification if there is misclassification in the data? Yeah, the answer is yes. So we show that if you have these semi-parameterizations, okay, you take the false positive rates to be equal to probably the misclassification divided by the propensity score, and false negative to be equal to the misclassification rate divided 1 minus the propensity score. Then you don't have to worry about misclassification in the data. What you will get, the true propensity score would always be equal to the observed propensity score. Okay, so there are situations under which misclassification will not affect the standard MT that we know in the literature. Okay, so I'm going to conclude here. We have some empirical illustrations, but I don't have time. So thank you for your attention, and thank you for this. Yeah.
Thank you, Desiree. Do you have any questions?
Desiree, you're going to see where my questions are coming from in a second, right? But your paper, it is mostly an identification paper, right? So you're not very much worried about estimation and inference, right?
That's true. Yes. True.
Yeah.
Yes. Yes.
And how easy it is to compute those bounds? I mean, it's just plug in, right?
Yeah, just plug in. Everything just plug in, yes. Estimate the observed propensity score. So we estimate that use local linear, and then we parameter. So when we use local linear, you see here there is a lot of noise, right? But then we use the logit, then you see that the shape is less noisy. Yes. Yeah. So yeah, we just plug in everything. Yes. But for the MT, we use local linear, and we use the LP robust package by Cataneo and co-authors. Yes.
Perfect.
We still have time for one more question. All right, I actually have a question. Just a clarification question, actually. If alpha bar is equal to 1, you still have non-trivial bounds, right?
Right. So that's a good question. So if alpha bar is equal to 1, the bounds that we have here, they are not changing actually with alpha bar anymore. And if alpha bar is strictly positive, you have the same bound, whether it's 1, whether it's half, same. So
but like it will not be like the entire real line, right?
Yes,
it's non-trivial.
Yes. So yes, so if it's equal to 1, you still have the same bounds here that we have here. You see, so those bounds here, they are not function of the alpha bar.
Yes, that is
maybe
true. Yes.
Implicitly through the data, right? But the formula is the same.
That's really nice. That's really nice. Thank you.
You're welcome. Yeah. And that's what we have here in the case of Ura's bound, right? Alpha bar is actually 1 because you are completely agnostic about the extent of the misclassification.
That is true. That is true. Thank you.
You're welcome. So should I stop sharing now?
We have 30 seconds for a question.
Okay.
A quick question, maybe.
Desiree, you have to estimate the propensity score, right? But the propensity score, does it depend on the misclassification rate as well?
Yes, so actually the observed propensity score is misclassified, right? It can be that it's a mixture of the two, right? People who are telling the truth, truthfully reporting, and people who are misreporting, right? Yes. So everything that we are doing is we use that information to partially identify the MTE. That's where the partial identification is coming from. Yes.
All right. Thank you, Desiree. Now, if you can stop sharing so that William can share his presentation. All right. Julian will now present his paper, and the floor is yours. I will tell you when we are like at the 14 mark. You're muted.
Can you see my slides?
Yes, we can see your entire screen. So if you
Yeah,
use the full screen button, we should be fine.
yeah, I don't see them. That's the issue. Wait, let me. Sorry about that.
No worries.
Oh, there it is. Okay, so
right.
I wasn't seeing them. Okay.
Yes.
Okay, thank you for the organizers. Thank you, Vitor, for organizing this session. So what I'm going to present here is this paper, Identification and Estimation of Unconditional Policy Effects of an Endogenous Binary Treatment. And this is joint work with my advisor, Isha, at UC San Diego. I have 20 minutes, right?
Yes, you do. With questions, 30 minutes. So if you can like try to stay like 15, 16.
Great, perfect. So let me introduce the problem a little bit. So here we're thinking about a thought experiment. We're thinking about a policymaker that wants to alter the distribution of some target covariate. And the question I want to ask is, how does this affect the unconditional distribution of the outcome, provided there is some relationship between the covariate and the outcome? For example, if we care about the mean of the outcome, we would take a look at how this affects the conditional means and then average them up to the unconditional mean. But for other functions like quantels, the relationship is not straightforward. So what we argue is that we have to directly estimate the unconditional effect. In this presentation, I'm going to derive a general form of the effect and show the identification, but then I'm going to focus mostly on quantels, and then we're going to show the connection to other functions such as the mean. So in this very general formulation of the problem, we have an outcome, y, which is related to some covariate binary, which is d. It's going to be treatment indicator. W are other covariates, and epsilon is the error term. And consider a situation where you are actually able to, in a sense, replace that binary covariate by a different assignment that I call the delta, where this assignment satisfies this condition here, which means that the proportion of people in their treatment now it's delta more than it used to be. So we want to increase the rate of participation. So when we do that, we have a counterfactual outcome, which is going to be given by this equation here. So the goal is going to be compare the quantels of y delta to y, or in general of some function of y, as this participation rate goes to 0, the change in the participation rate. So this question has been put forward and answered in this very influential paper by Firpo, Fortin, and Lemieux. To answer this question, they introduced the method of unconditional quantal regressions. They focus not only in a discrete covariate, but also in a continuous covariate. In the case of discrete, their framework doesn't allow for endogeneity, or at least under endogeneity, it's likely that their identification conditions break down. So actually, this paper started as an effort from my part and my advisors to try to understand better this paper when the ideal identification conditions break down and what was happening there. Some further results along the line of the paper of Firpo, Fortin, and Lemieux provided in a few papers by Christophe Rothe. In this paper, we're going to trace connections to the marginal policy relevant treatment effect of Carneiro, Heckman, and Vitaklil, and also to the MT framework of Heckman and Vitaklil. And then I've also been doing some work on this, where I, in the case of a binary endogenous regressor, I propose a sensitivity analysis in the method of unconditional quantal regressions. So this is like a very brief literature review of where this falls. So I'm very thankful of being second to present, because Desiree has done a great job of presenting the MT framework for me, so it saves a lot of time. In this paper, we're going to allow for treatment status to be endogenous, and we use the usual threshold crossing equation, where PW here is the propensity score. And you select if your propensity score is greater than these quantiles of the cost function, which is usually uniform 0, 1. So what is that we're interested in? Our parameter of interest is what we call the unconditional policy effect, and for the functional rho, and this is a marginal effect, because we're going to take this sort of derivative here of what happens in the limit to this effect. What is the general strategy to try to, wait, sorry, my screen is very small, so I don't see what I'm actually doing there. What is it we're trying to do? So the general strategy to enable to try to identify this function, this parameter is going to be, we're going to linearize this unobserved counterfactual distribution around the true distribution. And then we're going to use, so this is the derivative. So we're going to combine this linearization here with the fact that derivatives are linear as well. So that's going to allow us to get a nice result. So if I want to write this this difference here, then I can do the usual trick of just putting here where I stand, and here is the gap, and then hope that as delta goes to 0, this quotient here somehow converges uniformly to some CDFG. So in the limit, this is going to give us that the effect has to be the influence function evaluated at G, or the derivative influence evaluated at G. So what I want to show now is how to perform this linearization. And the trick has to be, it has to be uniform in order for this to hold. So this is the first result. So under some regularity conditions that I want to, I didn't want to bore you with that. We obtained that you can actually express the counterfactual distribution as being the original distribution plus delta times some gap there. So that in a sense of a derivative, right? Or a mean value theorem. And this gap depends on this term here, which is just not very interesting. What this first term here is capturing the fact that when you move the rate of participation, some people move from y0 to y1, and so this is the gap that is capturing that. But then what's interesting is this term here, which is what we call the derivative of the propensity score, and it's defined here. It's how the propensity score changes when you have a marginal change in delta equal to 0. And then this remainder here of this linearization is uniformly going to 0. So if we use that, we can plug in everything, and then that's our expression for the unconditional effect for some general function whose influence function is given by that phi there. And then if we interchange the order of integration, we can actually define an empty curve, which is defined as the expected value of the influence function of y1 minus influence function of y0 conditional on the level of indifference and for a given covariate. So what we can write is we can write the unconditional effect as this weighted average of this empty curve for the rho functional times this derivative of the propensity score, and then we integrate along the covariates W. This is clearly based on there's no surprise, this is based on the empty curve that was introduced by Heckman and Bithaclil. In the case of the mean, the influence function is just itself. So I would just here plug in y1 minus y0. So what we try to do here is to do something a little bit more general. So once you have this result, you can use the usual machinery to identify this curve. So the rest of the paper proceeds in the following fashions. I'm going to provide an analysis of this brief analysis of this term, which is the derivative of the propensity score. And then I'm going to focus on the quantiles in order to extend this paper of Firpo, Fortin, and Lemia to the case of endogeneity. How many minutes do I have, Victor? You're muted, sorry.
5 minutes and 30 seconds. You
5
still
minutes.
have a lot of time, I would say so.
Okay, fine.
Plus the time for questions, of course.
Oh, okay, yeah. So what happens when we move when we try to move, when we intervene the propensity score so that people move, so that we increase the proportion of people that are in treatment. So we have that originally in this line here. This is where people are indifferent. And this is where UD is equal to PX. This should be PW, sorry, in this line. So in a sense, we manipulate the propensity score in a sense that now these are the marginal individuals. And so these people that are in gray here are the people that were not treated before and now are treated. So what is exactly this derivative of the propensity score? Is this height here, in a sense. So delta times the derivative is this height here. So that's the proportion of new entrants. So this derivative of the propensity score is telling us at different levels of the covariate, what is the impact of this marginal policy. So the effect depends on this derivative of the propensity score, and this is measuring the relative contribution to the overall improvement in the participation rate for those who have a given value of the covariate. Unless this derivative is constant, not everybody contributes the same. So it depends on your value of the covariates. And then more interestingly, this is actually integrating to 1. So the intervention can be seen as modifying the distribution of covariates from this to P dot times F of W. But you have to be a little bit careful there because this PW could be negative, but still is going to integrate to 1 across the covariates. So now what I want to analyze a little bit is what happens if I take the function to be the tau quantile, and now I'm going to denote this effect as pi tau. So now I'm in the setting of Firpo, Fortin, and Lemia. So it's the setting of Firpo, Fortin, and Lemia plus a threshold crossing model for the treatment status, which is not something that they consider, but it's something we add in this paper. So what we find is that if that is the case, then your quantile effect here can be decomposed as an apparent effect and a bias. And so this apparent effect is actually the estimator that's proposed, the estimand proposed by Firpo, Fortin, and Lemia. And there is a residual bias that is given by not accounting that people select into treatment in this threshold crossing fashion. So the bias can be further decomposed in 2 terms. The first one we call a marginal heterogeneity bias. So why do I call that? Because if these CDFs that are here, which can be seen itself as treatment effects for the indicator function, if they do not depend on W, if they're not heterogeneous across W, then I could pull them out of the integral and then this would integrate to 0. So that bias term would be 0. What's interesting is that, and this is something also that motivated our research, is that in this threshold crossing model, even if treatment is exogenous, I mean, I have no correlation between the selection equation, the error in the selection equation, and the error in the outcome equation. You could still get that the participation rate is heterogeneous, so you could still get a bias. So you really need to account for how people select. And the second term in the bias is what we call a marginal selection bias, because we call it marginal because it's comparing people whose selection is to select into treatment versus the people who are indifferent, the same here. And so it has sort of differences in difference interpretation. So it's this difference for the people that were not treated in the first place minus the difference for people that were treated in the first place. And that's also contributing to the bias. And this bias term is the one that's going to dominate if the other one is 0, of course. So what is the marginal treatment effect for the tau quantile? It's based on the influence function for the quantums, which you will recognize here. This is the tau quantile minus the indicator over the density. And So this is very nice because some of the taus there, they cancel each other. So we get this nicer expression here for the marginal treatment effect for the tau quantile. And now, as usual, we're going to partition our covariate space with X and Z is going to be excluded for the outcome equation, and it's going to be our our IV. So using the idea of local instrumental variables and something close to that paper by Carneiro and Lee, we can show that we can actually identify this by doing the usual local approach. Moreover, this derivative of the propensity score, we can show that it's also identified by this ratio here. So if we put everything together, we get that the quantile effect can be identified by this expression here, where everything there is point identified, so the effect is point identified. So let me point out that it's a little bit hard to estimate, not only due to the fact that we have here a density that's evaluated at an estimated point, and it's in the denominator, which is always a little bit uncomfortable, but we also have to estimate this pair of average derivatives here. So it's a, I think last time I counted it's a 4-step estimation procedure, so it's not very nice. No, okay. So what we do in this paper is we introduce a new class of MTEs to analyze general effects, and we think they're useful because we can solve the case of quantiles, which is a very popular statistic that people care about. In the paper, we also provide some non-parametric estimation results, but estimating the effect for quantiles is much harder than for the mean. There is another reason for that. A lot of times, if you want to estimate, for example, the marginal policy relevant treatment effect, you might make an assumption that I think that the potential outcomes are linear, so that gives you a partially linear, right? So that doesn't work here because I'm taking the indicator of the potential outcomes as my definition of the MTV curve. So that doesn't work in this case. But still, you can add some parametric assumptions here, so maybe that can help you a little bit. But in the paper, we go with the full non-parametric estimation procedure. And that's it for me. You're muted, John.
Thank you, Julia. We have 3 minutes for questions. Do you have any questions?
Yeah, I have a quick questions. So why, how is what you are doing different from the policy relevant treatment effect parameter?
Yes, so if I consider the case for the mean, then I'm back exactly in the case of the marginal policy relevant treatment effect. So one of the contributions of the paper is to show that this, the method of unconditional quantum regressions and marginal policy relevant treatment effects are part of a larger class of family of parameters, and they can all be analyzed by choosing a different influence function for what you care. If you care about the mean, you choose the traditional MT function. If you care about the quantiles, you choose the influence function of the quantiles. One thing that is interesting, actually, if the support of the outcome is unbounded, the mean is actually not Hadamard differentiable. So you need to go through another route to show that they're part of the same policy. You need to add some domination conditions, but in practice, I have a hard time thinking about any outcome in real life that's not bounded.
So, but in the derivation, you are allowing the support of Y1 and Y0 to be different.
Yes, exactly. So here, the key result, which is here, it holds uniformly over the union of the supports. Okay. So I don't care about if they're bounded.
Right. Do we have more questions? Right. Thank you, Julia. Great presentation. I really appreciate. Pedro, the floor is yours.
you can all see my screen, right? I hope.
Yes.
So yeah, first of all, let me clock myself as well, because I talk a lot and 15 minutes is never enough for me. So yeah, so first of all, let me thank like Victor for putting up this like very exciting and like entertaining session, and thanking all the organizers and everybody in the audience for taking the time as well to have us and listen to what we have to say. Right. So today I'm going to talk about something that usually is new to me. Right. So I'm very honored to share this session with so many like specialists on MTE. I'm a beginner on MTE. Right. I mean, and this work that I'm going to present today is joint work with Minhai Mao. He was a PhD. We share the same advisor. He was a PhD student at Carlos III in Madrid, and so did I. Right. And today the main idea of this talk it is to propose tests for the underlying assumptions behind the marginal treatment effects model, right? And I'm Pedro, I'm a senior researcher at Microsoft, and I'm on leave from Vanderbilt. Good, motivation, right? So first, I'm gonna start, I mean, I know 99.9% of the people around here are very familiar with the topics, but I'm gonna step back and provide a big picture, right? So first, MTE, right? What's the main idea of the MTE? It is to somehow extend this like Nobel Award winning like research line like proposed by like Ibis and Angrist in the early 90s about the local average treatment effect, right? And the idea like first is why do you want to extend that? Right? So the way I think it is, well, we know like late, it all depends on the instrument. You're gonna get an estimator for the average effect or the distribution effect. For the compliers, to define compliers, the compliers are instrument specific by definition. So if I have an instrument running around that is not what I really care, right? I'm perhaps gonna get an answer for a subpopulation that may not be the main population of interest, right? So, but on the other hand, the beauty of like having this instrument specific policy relevant parameter, right? It is that the underlying assumptions to identify this parameter is fairly weak, right? So you essentially for binary treatment, you only require a binary instrument. But for me, the question always comes first, right? So if I care about something, I mean, I care about that for some reason. So in order, I don't want to like kind of like move the goal. And if that is the way I'm thinking, the MTE come to rescue what I'm doing it, right? So the MTE introduced in a series of papers by Gene Heckman and Ed Vitoracil, right? And the idea is like, well, we don't want our like statistical technique or data availability to dictate the questions that we can answer. That comes with a cost, in like at least in the theory part, like it is that we're gonna require instruments to have more variation. So essentially, we're gonna have continuous instrument with large support if you wanna indeed provide precise answers for a very large class of parameters, right? But that's the trade-off you're facing. This paper, I'm gonna marry the MTE, right? And because interesting, once you abstract away from these debates about policy relevant and all that, the underlying structure between the late and the MTE is fairly similar in terms of assumptions, right? So both of them are gonna exploit some type of IV monotonicity condition and some type of IV exogeneity conditions. And why this is important for me, right? This is important for me because if you open in the literature, like especially the paper by Toru Kitagawa in 2015, right? He derived a sharp set of testable implications for the late setup, right? When we have a single discrete IV that satisfies both the IV monotonicity condition and the IV exogeneity assumptions, right? So what I'm saying here that like Kitagawa 2015 have shown to us that like, well, even in the just identified case, we can falsify our model, right? We can falsify the late setup. And he also proposed a way to do this in practice, right? Using simple in quotations, right? Statistical tools to falsify our late assumptions. I mean, this, of course, is not the only game in town, right? So Murifier and Wang also have a very nice path-breaking contribution in the same setup. But what I want to call your attention here is that like this is essentially for the late setup, right? So for like discrete IVs. Then when I was reading this literature, I have the following questions together with Minghai. Can we do something here that is similar with a continuous instrument, right? Can I do something here similar, not only for continuous instruments like the MT, But what happens if I have multiple, quote unquote, potentially continuous instruments? And how I can do all this in a unified way that is easy to incorporate covariates, right? And incorporate kind of like same parametric restrictions into the model. So this is the kind of the leading question that I want to try to do here. Think about Kitagawa 2015, right? Can I do something similar that he has done, but for the MTE setup? And when I do this, I want to do it in a unified way that we can consider a large class of MTE models, right? In the sense, depending on the model assumptions, we're going to superimpose on top of the IV assumptions. So the way I think about our contributions in this paper, right? And I mean, it is first, we go back to Heckman and Vitlasil 2005, right? We read that paper very carefully. And in that paper, they state that the MTE assumptions are actually testable, right? So they say like, oh, we have a monotonicity testability restriction there. You have an index testability restriction that. This was also the starting point for like Toru's paper, right? And Toru showed this is sharp in the binary like instrument case, right? We come here and show this is also sharp in the continuous case. I view this as a very modest first step. This is just a kind of a sanity check to make sure that we are like, for my paper, this is a sanity check to make sure that like we're actually exploiting everything that we can to test our models, right? So we build on Toru's work, we build on Heckman, Vitlasil, we build on like Victor's and Desiree's and Otavio's paper as well. We have a lot of things that are there. This is the first step. But that's kind of like, in our world, is a foreplay. Because we derive the testability restrictions, then how I can map these testability restrictions to the data, in the sense, how can I construct like tests for the sharp testable implications? And if I'm talking about tests, right, I cannot stop on just identification result. I have to talk about estimation and inference. And that's where the big animal lives in this world. Because, I mean, you're going to have to handle and acknowledge that propensity score are going to be estimated using parametric, semi-parametric, or non-parametric methods. We're going to have to acknowledge the testing shape restrictions involves maps. They are not very differentiable, not very smooth. So we're going to have to take into account that I cannot apply off-the-shelf delta method arguments to compute critical values. And this is where our main contribution is going to live in, right? So how we can actually bring those testable implications to the table, write software so applied researchers can click and run this as we talk. Right, so setup, right? So this is essentially, I mean, if you have to leave this talk with a new message, like Mao and Santana, what we are doing it is essentially proposing a statistical test for the sharp testable implications of the MTE model, right? And doing this, it's very easy to say, very hard to prove, right? So I'm very grateful that Minghai, it is the main driver of the theory here. I'm the applied like co-author in this paper for the first time in my life, which I quite enjoy. So talk about setup, right? So starting point, let's think about the classical MTE model, right? I have potential outcomes Y1 and Y not. I have non-separable models that depends on covariates X and an observed heterogeneity V1 and V not. And we have like a selection equation D, which is going to depend on like mu D Z here. Z is a vector of combining X and excluded instruments and some unobserved heterogeneity as well. So this is kind of like a Rice selection model, a generalized Rice selection model, right, with a latent index for treatment decision. So this is not very helpful because it does not impose so much structure as I want to, right? So because I mean, we can always write things in this way because I'm not restricting how these V's relates to each other, right? So what I'm gonna do next, it is, well, let me add the MTE assumptions, right? The first one has to do with the single threshold crossing condition that so both Desiree and Julian talked about a second ago. And essentially, instead of having this non-separable index restriction, I'm going to be able to split like whatever comes with Z, whatever comes from U on separate sides, and U here is going to be continuous, right? I mean, you can even assume that U it is uniform. Then instead of having this V here, I'm going to have a propensity score, which is what everybody has talked about so far. On top of this single threshold condition, which is kind of like quote unquote monotonicity, right? If you relate this to the late assumptions, as Ed has done, we're also going to impose this IV exogeneity condition that the excluded instruments are independent of the unobserved heterogeneity affecting the selection equation and the potential outcomes given covariate X, right? So once we have those structure, I mean, you can use local IV to recover the MTE curve for each like U, like with this unobserved heterogeneity in the selection equation and each covariate value X, right? And in practice, you can think about, well, we can do this in theory, right? But in order to actually do this for all possible values of U, you're going to have to rely on a very strong support condition, right? But for each value of X, my instrument varies from like enough such that I can recover the propensity score in the entire like 0-1 interval. In practice, this is hard, right? So usually what we're going to do, how we move forward, we're going to add more structure, right? Which is what Julian was mentioning a couple of minutes ago, either a partial linear model, either, a linear model per se, right? That's how I'm going to move things as well, right? So this is essentially what several other authors have done in the literature. And in this paper, what we're going to do, if you want to move in this direction, we're going to assume a linear index, actually a linear model for the potential outcomes, right? But we're going to keep the selection equation flexible, right? So it's kind of asymmetric, right? But hold that thought for a minute. So linear model, betas can differ. And here the index model, right? What I'm going to do, I'm also going to impose this separability condition like before. Right? So, but here it is not only linear model. We are also essentially assuming that our errors here, V1 and V0, they are not only independent of, they're not only independent condition on Z, now they're fully independent of Z and X. This buys us a lot in terms of support condition, right? And also this allows us to get something slightly more flexible because now Z does not to be continuous. It can be discrete as long as I have one continuous covariate. But that's not new. People have discussed this in the literature. So first thing we do in the paper, right? So we say, let's first focus on the non-parametric model, right? And we're going to emphasize covariates everywhere. So original paper, 2005, Heckman and Yggdrasil, they showed you have two testable conditions, right? Two set of testable conditions. The first one is the index efficiency. The second one is the monotonicity restriction. Index efficiency is essentially telling that instead of conditioning on several instruments here, Z, so I can replace it by a propensity score. So this is pretty much a non-parametric significance testing, right? I come from the literature on specification testing, so I see this as a non-parametric significance test, right? We can manipulate things like this. This is only binding if I have several instruments, right? If I have a single instrument, this is like, poof, doesn't matter. We don't do it because it's just P, it is just a monotone transformation of Z, and then you don't lose any information by doing this monotone transformation. Second one is more fun because it's a monotonicity restriction, it's a shape restriction, right? So essentially we're telling like, well, these modified outcomes here, it is increasing in P, the propensity score for each value of X. And if you flip the coin, right, look for the comparison group, this is going to be decreasing in P with propensity scores. We can play around with these Borel sets, close intervals or short, like half intervals, doesn't matter. We do this, and this is like essentially show the first step of the paper. This is actually, without further assumption, this is all you can actually test, right? I mean, not surprising, right? But it's sanity check. Second result, say fine. Nobody that I know gonna ever use this in practice, this model, because of X, right? The assumptions are very strong for the support conditions. So if they're gonna use our parametric models, with what's the analog of those testable conditions, right? Essentially, we have the index restriction, we have a monotonicity restriction as well, right? And we show in the paper that under our assumptions, like under our structure of the MTE model, assumption 3, right? Those analogous to the IV, these are sharp testable implications as well. which is good because like we can essentially do similar tricks to tackle the non-parametric case and the semi-parametric case. But as I said, right, this is kind of like for us, it is the only first step. It is the beginning. So I'm gonna talk only 1 minute now because it's the test statistic. Essentially, how you can do this, right? The index restriction, if you estimate propensity scores here semi-parametrically or even parametrically, and you use a smoothing test, you can ignore entirely the estimation effect because the bandwidth, this distance is going to converge fairly slow. It's lower than the parametric rate, right? So you can ignore estimation effects of P. What's the catch? Those tests requires a lot of data because they depend on the smoothing, right? And if I have many covariates X here, this is going to be like cursor dimensionality are going to kick in and destroy my test. This is what we have done so far. It's essentially exploiting Lito and Gonzalo. There is an alternative path, right? Which is rewrite that as an integrated moment condition. So use tricks similar to what Julian actually used, right? Recharacterize that null hypothesis in this particular way. What is the catch now? I have to estimate propensity scores, right? And now the estimation effect is non-negligible. It enters in this equation in several different ways. We are currently working on this to get the influence function of this wild animal here, right? Exploiting the tools of like Han and Reader of the influence functions for semi-parametric generated covariates. Then, fine, we do this, we can test it. As soon as we get this influence function ready to go, we are almost there, right? This is a work in progress. We're gonna be ready to go. Shape restrictions are also cool, right? Testing monotonicity here. If I don't have covariates, you can do this as in Anders and Shi, right? I think this is what, or you can also do the other types of moment inequalities because shape restriction like this can be expressed as a continuum number of moment inequalities. But if you have covariates X and estimated propensity scores, those tools don't apply automatically because I don't know how to handle estimation effects on these guys. So what you're gonna do, right? You're gonna translate this propensity, these monotonicity restrictions here as a concavity restriction by playing around with copulas, right? And once we play around with copulas in this way, we can use this least concave majorant because that's the characteristic that is an if and only if condition because we have continuous propensity score, right? So once we do this transformation, right, essentially our test is gonna look something like this. So what is the least concave majorant operator? I have some curve that is like this, ups and down, right? I apply this map that's gonna get the least concave curve that is above, and we're gonna measure this distance between the dashed line and the solid line. If this distance is quote unquote large, we reject. If it is small, we don't reject. What is the catch, right? Catch is that this operator is non-smooth, it is non-differentiable, right? So you cannot apply delta methods to compute critical values. You cannot apply delta methods to get critical values. Classical bootstrap is not valid, right? We are in this world of directional Hadamard differentiability. We have to use different tools. What we have done, let's replace the bootstrap, classical bootstrap from the numerical bootstrap by Hong and Lee, right? This requires us to choose these numerical derivative steps. It's not insensitive to these steps. So this is like the elephant in the room. But we can bypass all the technical challenges by doing this. Once we do this, we have a test statistic that works in practice and theory is valid. We have simulations, we are finishing applications, and I'll stop right here. Thank you. You're muted.
I'm forgetting about that all the time. Thank you, Pedro. We have 1 minute for questions. Do we have a quick question?
So Pedro, yeah, it's nice talk, clearly explained. I have just one quick question. So forget about covariates. Okay.
Yes.
So then it becomes the test is like testing the index sufficiency and then the monotonicity of the.
You can test them jointly or you can test them separately.
Jointly, right?
Yes, yes. To test at sharp test implications, you have to test them jointly.
Okay, so you are testing it jointly, right? Because you're taking the max of these two statistics.
So yes, so that's why we are doing this new test for index condition because I mean, this is gonna convert at square root n, and it's the same rate for this concavity test, right? So by doing this is important because I have the same rate for both tests, so you can test them jointly easier. Right now in the paper, if we're using this like index sufficient using the smoothing tests, and that's nightmare because this converges lower than root n, this converge at root n, so I have to do corrections for multiple testing because I mean, even though both are asymptotic normal, the rate of convergence are different, and that was very unpleasant, right?
Yes.
So
If I want to test only the monotonicity condition, there is
You
the
can as
paper
well.
by Shi and Yuchin Su that test the generalized monotonicity. So can you use the test statistic and then bid on that?
if they have estimated propensity scores, right?
Okay,
It's
okay.
the tricky part. If they don't
I
have
see.
estimated propensity scores, I can use
Okay,
off the
I
shelf.
see. Yeah.
Yes.
Okay.
My test is going to be our test is going to be slightly different because I mean, in general, we can gain some power by looking at the integrals here, but those are not super important. But you can use under the sheet if you don't have covariates and propensity scores. I mean, and you don't have propensity scores, you have the observed instruments. Then just go off the shelf.
Okay. Thank you, Pedro.
Thank you, everybody, and sorry for going over time. I knew it was going to happen.
No worries. I really enjoyed the presentation, and I will actually talk to you later. I do have a question, but I'll talk to you later. Let's share my screen. This one should do the job. All right. So first of all, thank you all for coming. I'm really happy that we have a large attendance. So thank you all for coming. And I'm Vitor Possebon. And today I'm going to share with you my research paper, whose title is Crime and Mismeasured Punishment, Marginal Treatment Effect with Misclassification. And at this point, I would like to start with my empirical question. I'm interested in analyzing the effect of alternative sentences on reoffending behavior. So basically, we have a defendant, so a person who committed a crime, and this person will receive a treatment. This treatment is an alternative sentence. Basically, it can be either a fine or a community service. Or in the case, the control group didn't receive any sort of punishment. The person was found not guilty. And I'm interested in analyzing the effect of an alternative sentence on the outcome variable. And this outcome variable is whether the defendant was prosecuted for another crime within 2 years after the final sentence in their case. And in order to answer this question, I collect data from the state of São Paulo in Brazil between the years 2010 and 2017. And as a preview of my results, I would like to highlight that the effect of alternative sentences is very heterogeneous. It can be positive, 0, or negative, depending on the value of the observable covariates and the unobservable latent variable. And now that I have explained the empirical question, I would like to explain the theoretical challenges behind my approach. So basically, in order to answer this question, there's a standard strategy in the literature. Basically, we collect information about the trial judge's sentences, and we use the trial judge's sentences in order to define our treatment variable, basically whether the person was punished or not punished with an alternative sentence. However, by focusing exclusively on the trial judge's sentence, we have a misclassification problem. And this misclassification problem happens because in any criminal case, the defendant or the prosecutor may appeal. So if any part disagrees with the judge's decision, they can appeal to another court, and the following court, the appeals court, may overrule the trial judge. And as a consequence, if we are defining our treatment variable based on the trial judge's sentence, there will be possibly a misclassification problem if the appeals court overrules the decision. And as a consequence of this misclassification problem, as Desiree already explained it, we have a non-classical measurement error, and this is quite complicated because our estimates will be biased, and this bias can actually go anywhere. And it can even move your estimates further away from 0. So we are not in that beautiful world with attenuation bias. Like, life is complicated here. And given that, we have to think about possible solutions. And one solution is to actually acquire better data. And I'm able to do that in my empirical part. I collect information about the trial judge's sentences and the appeals judge's sentences. And as a consequence, I can actually use the true treatment variable in order to estimate the true MT function and use that as a benchmark for what happens when we ignore the misclassification problem, and also to evaluate whether my new solution actually works. So besides acquiring better data, I also propose a new method. And this new method uses information only about the trial judge's sentence, so only about the misclassified treatment variable, but actually accounts for misclassification, allowing us to identify some features of the MT function. And at this point in time, I would like to briefly explain what I'm doing here. So basically, in this new method, I'm going to restrict the relationship between the misclassified treatment variable, the correctly classified treatment, and the instrument in order to derive bounds around the MT function. And right now, I'd like to briefly explain my contribution to the theoretical literature, and I'm actually going to focus on the differences between my paper and Desiree's paper. Desiree's paper is by far the closest paper to mine. He already did a great literature review, so I can skip all that. And I really like Desiree's paper, but we are doing different stuff. And why are we doing different stuff? Basically, each empirical question, each empirical problem may have different identification challenges. In particular, I'm going to show to you that in my application, my instrument is not independent from the misreporting decision. So I do require different identifying assumptions. The assumptions that I'm going to impose, they have a sensitive analysis flavor. So basically, it's as if we started in a world without misclassification, and then we ask, all right, what happens if we allow a little bit more of misclassification? And what kind of conclusions we can achieve by allowing for more and more misclassification? And this is a partial identification paper, so let's understand first my notation, then my assumptions, and then how I derive the bounds. In terms of notation, I'm following, I have a notation as standard as possible. Z is my instrument. This is the trial judge's punishment rate. So basically, how tough the trial judge is. U denotes the resistance to the treatment. And in blue here, I have everything that is related to the true treatment, basically the punishment according to the final ruling in the case. And PD denotes the correct propensity score. Y0 and Y1 denote my potential outcomes. That's the potential reoffending behavior of my defendant. And in red here, I have everything that is related to the misclassified treatment variable. That's the trial judge's decision. And PT is the mismeasured propensity score. And given this notation, I can define my target parameter. And my target parameter is this theta function here. I'd like to emphasize that this is a slightly modified version of the MT function defined by Heckman and Vitlaciu. And the drawback of this slight change is that my theta function actually depends on the instrument. So it's not policy invariant. However, I would like to emphasize that this theta function is still interpretable as a marginal treatment effect. It's basically capturing the average effect for the defendant who is at the margin of being punished according to the punishment criteria chosen by, used by Judge Z. So I fix the judge and I look at the individuals who are at the margin of being punished by that judge. And I can also define the local instrumental variables estimates. And in my paper, I have the misclassified treatment variable that focuses on the trial judge, but I also have the true treatment variable that uses the final ruling. So I'll have two local IV estimates. The first one uses only T, the misclassified treatment variable, and I follow the definition by Shalat, and I define this local IV by this ratio, and I denote it by F of Z. When I actually observe the true treatment variable D, I define a similar local AV and I denote by F star. And the goal of this paper is to connect the local AV estimates to the theta function, to my target parameter. And at this point, I would like to analyze the bias of the local AV F. So basically, what happens when I ignore misclassification? To analyze this bias, I require 4 assumptions. My first assumption is the independence assumption. I'm not imposing anything about my instrument and the misreporting decision here. I also require an assumption about the strength of my instrument, and I also require 2 regularity conditions. And given those 4 assumptions, I'm actually able to show that the leave estimate that uses only the misclassified treatment variable is biased. And the bias is actually given by this formula here. As you can see here, we have a scaling factor. And this scaling factor is a function of my instrument. For that reason, it might be the case that the bias is positive at some points and negative at other points. So this is like the source of all the complications in this MT problem. That's the reason why the MT is actually more complicated and delayed. But I would like to emphasize that if we actually observe the true treatment variable, we are fine. This is an old result in the literature, and F star is actually equal to the MTE. So since I do observe D in my data set, I can use this result as a benchmark for the naive analysis that ignores misclassification, and also for my partial unification strategy that I will explain right now. So basically, I want to derive bounds around the MT function. To do so, I will impose a ratio restriction. Here, I'm basically saying that the derivative of the true propensity score is similar to the derivative of the mismeasured propensity score. And I'm saying that this similarity is bounded by this known constant C. Theoretically, I do impose that this constant C is known, but in the paper, I actually offer some ways to choose to approximate this constant using data. And here, I would like to emphasize that if I impose that C is equal to 1, I'm basically imposing that there's no misclassification. And when I increase C, I'm weakening this relationship, this restriction, and I'm allowing for more and more misclassification. And with this assumption, I'm actually to derive uniform bounds around the MT function. Those bounds are given by this set. And this set depends on the local AV estimate that uses only the misclassified treatment variable, and it also depends on the constant C. They look somewhat ugly, but they are actually quite easy to compute and estimate. It's just a if condition in R, so that's actually very easy to estimate. And importantly, those bounds are uniform. The uniform condition is here, but for the interest of time, let's not spend much time here. And I would like to spend the last 5 minutes of my talk actually focusing on my empirical application. So let me briefly explain my data set. As I mentioned, I want to analyze the impact of alternative sentences on reoffending behavior. And my treatment variable is whether the person was punished with an alternative sentence or not. My outcome variable is whether the defendant reoffended within 2 crimes after the final ruling in their case. And my sample contains all criminal cases in the state of São Paulo whose maximum sentence is less than 4 years. Basically, I focus on this type of crime because by Brazilian law, those crimes cannot be punished with incarceration. They must be punished with an alternative sentence or not punished at all if the person is found not guilty. And my sample covers the entire period from 2010 to 2019, but I actually focus in the period until 2017 because the last 2 years are used to define my my outcome variable. And at the end, I have 43,500 case defendant pairs. I also need to, I have text data, I have like full sentences, and I have to read those sentences and define my treatment variables based on text analysis. So basically to do that, I use a logistic lasso. For the misclassified treatment variable, I only use a logistic lasso for the trial judge's ruling. But in order to define the correct treatment variable, I use a logistic lasso for the final ruling. Moreover, my outcome variable is defined using a fuzzy matching algorithm of full names. Unfortunately, I do not observe anything else but full names. So that's the only thing I can do. But I will have some like robustness checks where I will focus on subsamples with longer names that will avoid like misclassifying of the outcome variable, misclassification of the outcome variable. My instrument is the leave one out mean. It's basically the trial judges punishment rate. I only use judges with at least 20 cases, and I only use court districts with at least 2 judges. And right now, I'd like to show the relationship between the misclassification decision, the misreporting decision, and my instrument. So let's focus here on the light blue line. This is the probability of misreporting, the probability of a misclassification error, given the value of my instrument, given the leniency of my judge. And as you can see here, this line is not flat. So those 2 variables depend on each other. And they do require new assumptions in order to understand, in order to answer my empirical question. And finally, I would like to cover very briefly my empirical results. Let's start with my first stage regression. Here, I'm estimating the true propensity score. And I tried 3 models. I tried a linear model, a quadratic model, and a cubic model. So basically, the propensity, the final decision of the case as a function of the judge leniency rate. And as you can see here, the linear model is actually doing quite a good job. My instrument is very strong. No one will complain about the strength of my instrument here. And I can also compare the true propensity score against the mismeasured propensity score. And as you can see here, misclassification is not very large in my problem. So both propensity scores are similar to each other, but they are not exactly the same. So there's some room for misclassification bias here. And I can actually compute the smallest possible C for my assumption 5. And this value is 1.02. But just to be safe, I actually use a value of C equal to 1.10 when I'm estimating the bounds around the MT function. And now I'd like to show to you the MT bounds around the MT function, sorry, the MT bounds for the city of Campinas. Campinas is, in my sample, the city with the largest number of judges. So let's see the results for the city of Campinas. This is a city in the countryside of Brazil, of São Paulo. It's actually the 3rd largest city in the state. And here we have the results for Campinas. The orange line is the estimate of the true MT function. So this guy is actually using the true treatment variable D. And as you can see, it's a decreasing function. But the most interesting aspect that I want to analyze here is actually the bias, the misclassification bias. So let's compare the orange line against the dark blue line. The dark blue line is the leave estimate, the estimate of the leave estimate that uses only the misclassified treatment variable. So the dark blue line is what we'd see if we ignored misclassification completely. And as you can see, the bias is actually quite complicated. It starts negative and then it becomes positive, showing that the bias can go anywhere. So it's hard to interpret the bias beforehand. And here in this graph, I also have the bounds that uses my ratio restriction. The bounds are given by the light blue lines. And as you can see, they safely contain the orange line. So they are actually doing quite a good job. And they are also very tight. So that's good. I can actually for example, in this case, I can actually say that the MT function is positive. And to conclude very briefly, I have 3 key takeaways. First of all, my paper, similar to Desiree's paper, focus on partial unification of the MT function when there is misclassification. To derive the bounds around the MT function, I impose restrictions on the propensity scores. And finally, in my empirical application, that analyze the impact of alternative sentences in the state of São Paulo, Brazil, I actually find that the bias can go in any direction, making it a quite complicated problem. And right now, thank you for coming. And if you have any questions, feel free to ask them.
So Victor, just a quick question. In your case, I mean, the misclassification is always in one direction, right? Because I mean, does that help you a lot? That's why you get so tighter bounds?
So actually, in my case, misclassification goes in both directions. It is larger in one direction. Most of the time, when a defendant is found guilty by the trial judge, the defense appeals and is able, in 3% of the cases is able to reverse the decision. But I also have a few cases when the defendant was found not guilty, and the prosecutor appealed and was able to overrule the decision. So I have a misclassification in both directions. But the first direction is like 3.5%, and the second direction is 0.9%.
Vitor, sorry, Pedro, do you have another question? Is something that we should expect the decreasing form of the MTE, and could you explain that a little bit?
Sure. Let me go to this figure. Basically, this is saying that there's negative selection to the treatment. Yes, negative. Yes. Sorry. So it's larger for the people. So the treatment effect is larger for the ones who are more likely to be punished. So we actually have positive selection. In some sense, the way I interpret that is the punishment is basically reinforcing whatever was there beforehand. The judges will be more likely to punish people who are actually more dangerous, but it doesn't change the behavior of those guys a lot. And to be true, when I actually compute confidence bounds, everything is a beautiful zero. Just to be like very honest, with confidence bounds, everything is a beautiful zero.
Story of my life.
So Pedro, no, Vitor, sorry. So is
sure,
this
no
coming,
worries.
Is this coming from the parameterization?
All right. Do I have the non-parametric ones here? All right. I deleted the non-parametric, the semi-parametric estimators here, but I do have them, and it does suggest that the linear model works.
Okay. So yeah, I have a question. So, but essentially, even if your theta parameter is a function of z, once you move z around over the support of z, in the end, you're getting the same curve as Heckman and Vitellasi, right? Because
yes.
you will cover the propensity score support, and then the function that you're getting will be the same, right?
Yes.
So the curve, the MT curve is the same, even if the parameter at the given z is not the same, right? So it's like you're getting the MT, right?
Yeah, I would say I'm getting a rescaled version of the MT.
Okay.
So, like, if the propensity score was simply the instrument, I would get the MT function beautifully. But when it's like, for example, the propensity score is like alpha of z, then I'm shrinking the MT function in some way.
Yeah, but you're still conditioning on the propensity, the U equal to the propensity score, right? So in the end, you cover the support of the propensity score, right?
Yes, I do.
Yes. So now I want to look at your ratio restriction. So does that imply that, are you assuming that because this derivative here is always positive, right? So are you assuming that you have the same sign as the misclassified version of the MT?
Yes, in the full paper, I have a previous assumption that just says that those two things have the same sign, and they can identify the sign of the MT function.
Okay.
But I had to shorten the presentation for the 15 minutes.
Yeah, cool. I like the way that misclassification is changing with the instrument. So you observe the true, and then you observe also the version that is misclassified. Yeah, that's very good. Yeah.
Yes, that I would say that's one of the reasons why I collect this data. I spent a few $1,000s on that, so I'm quite happy that it worked. All right, so let me stop sharing. I would like to thank you all for coming. I'm really glad that we had questions for everybody. I really enjoyed this session, so thank you all for coming. And I hope you guys also enjoyed all the presentations here. Thank you.
Thank you, everyone. Thank you.
Thank you, Victor, for putting up the
Thank
session and all that.
I really appreciate that you guys accepting the invites, the invitations. I'm really happy that we had this amazing session.